Have you ever stopped to think about how your GPS just knows where you are? I mean, every satellite signal has errors, right? Or how a space probe can fly millions of miles and hit its target perfectly. Well, today we're going to pull back the curtain on one of the most incredible tools ever created for dealing with exactly that, a messy, uncertain world. We're talking about the Kalman filter.
All right, so here's the game plan. First, we'll look at the big problem, a robot's uncertainty. Then, we'll see how we can actually describe that uncertainty using a surprisingly simple idea, the bell curve. From there, we'll get into the predict-update loop, which is really the heart of the whole thing. And then we'll see what happens when things get a little messy and nonlinear, which they always do in the real world. We'll wrap it all up by talking about why this matters so much. So, let's really think about this for a second. Your phone's GPS signal gets bent by the atmosphere. A self-driving car's camera might be off by a few centimeters. The wheels might slip just a tiny bit. The point is, every single piece of information these things get is a little bit wrong. It's noisy. So how on earth do they take this constant stream of flawed data and build a picture of reality that's so incredibly precise? That's the big question, and that's exactly what we're going to figure out.
Okay, Section 1. The robot's uncertainty problem. The thing is, every measurement is a little wrong, and every movement is a little off. To really get a handle on this, let's imagine we have an autonomous underwater vehicle, an AUV. This thing's trying to navigate the deep ocean, where, GPS is completely useless. It's on its own, relying only on its internal sensors to find its way.
And this right here, this is the core of the whole problem. The AUV doesn't think I am this exact spot. No way. Instead, its position, what we call its state, is more like a fuzzy cloud of possibilities. It has a best guess, sure, that's the center of the cloud. But it also knows it's not totally sure, and that's what the size and shape of this cloud represents, its own uncertainty.
All right, next up, guessing with bell curves. So how do we represent what we know and what we don't with a powerful mathematical tool? The big question is, how in the world do you do math with a cloud of possibilities? It sounds like it would be crazy complicated, right? But the solution here is actually, well, it's surprisingly simple. It all boils down to a shape you've definitely seen before.
And yep, you guessed it. It's the Gaussian distribution, or what pretty much everyone calls the bell curve. The whole idea here is that we can represent all that fuzzy uncertainty with this one shape. And why is that such a game changer? It's all about simplicity. See, a bell curve is defined by just two numbers. The mean, that's the peak, our best guess, and the variance, which is just how wide the curve is. So a wide, flat curve, we're not very sure. A tall, skinny spike, we're feeling pretty darn confident.
And this is where things get really cool. This super simple idea scales up beautifully. So if we're just talking about one thing, like the AUV's depth, our uncertainty is that classic 1D bell curve. But what about its 2D position on a map? Well, now that uncertainty cloud becomes an ellipse. Yeah, the math gets a little fancier. We start using something called a covariance matrix, but the core idea is exactly the same. A best guess right in the middle, and a shape that tells us how uncertain we are around that guess.
Okay, on to the next section, the predict-update loop. This is the simple two-step dance at the heart of the Kalman filter. So we've got a way to describe the robot's state, uncertainty, and all. Now we get to the actual engine of this thing, this powerful, continuous cycle that is constantly making our guess better and better.
And it really is just a simple, powerful dance between two steps. Step 1, you predict. You take your last best guess, factor in how you've moved, and make an educated guess about where you are now. But with every prediction, your uncertainty grows. Then comes step 2, you update. You take a new measurement from a sensor and use that new piece of information to correct your guess. And when you do that, your uncertainty shrinks. Predict, update. Guess, correct. That's the whole algorithm right there. So let's watch our AUV actually do this.
So here's our AUV at the start. It has a general idea of where it is, but you can see from that big, wide uncertainty ellipse that it's not very confident. It's basically saying, I think I'm here, but I could really be anywhere inside this big oval.
Now for the first step, predict. The AUV fires up its thrusters and moves forward. It uses its internal model of how it moves to guess its new position. But look what happens to that uncertainty ellipse. It gets bigger, it stretches out. Why? Because that internal model isn't perfect. The thrusters aren't flawless. Maybe there's an ocean current it doesn't know about. So here's the crazy part. By just moving, without getting any new info from the outside world, the robot actually gets less sure about where it is.
But then,
it gets a new piece of evidence. Bam! The AUV pings a sonar beacon down on the seabed and gets a reading. This gives it another guess at its location. But, and this is super important, that sonar reading isn't perfect either. It has its own errors, its own uncertainty. So this new information is also a fuzzy bell curve of possibilities.
And this is the magic trick. This is the update step. The Kalman filter takes two uncertain things, its own blurry prediction and the sensor's blurry measurement, and mathematically combines them. And what you get out is a new, single estimate that is actually more certain than either of the two pieces of information that went into it. Just look at how that uncertainty ellipse has shrunk. It's tiny now, our confidence is way up, and we're ready to start the whole cycle over again.
Okay, Section 4, when systems get nonlinear. Because the real world doesn't always move in straight lines. Now, this all sounds pretty perfect, right? But there's a catch. The classic Kalman filter we just talked about, it has one big weakness. It only works perfectly if the system you're modeling is, well, linear.
So what does that mean? Well, a linear system is simple. It follows straight line rules, like what you see on the left. But the real world, the stuff on the right, it's nonlinear. It's all about curves. Think about the physics of a car turning a corner, or the way a drone flies, or even the math you need to figure out your position from a beacon. It's all curves. And when you try to apply the filter's pure, simple math to a curvy, non-linear world, they kind of fall apart. So that brings us to extending the Kalman filter. How do you use a straight line tool in a curvy world? We can't just give up on this amazing idea, right? Of course not. Instead, we use a really clever trick. It's called the extended Kalman filter, or the EKF for short.
Okay, so here's our problem in a picture. This big curve represents the true, messy, nonlinear reality of our system. If our robot is at one point on this curve, it can't just use those simple straight-line equations from the basic Kalman filter to figure out what's going to happen next. It just won't work.
So here's the trick. The EKF basically just zooms way, way in. At every single step, it looks at its current best guess on that curve and says, okay, if I look super, super close at just this one tiny spot, what does it look like? And you know what? It looks like a straight line, a tangent. So the EKF makes a local linear approximation. It basically pretends the world is a straight line, just for a split second, so it can use all that powerful Kalman filter math we just learned.
And this table really sums it all up. The standard Kalman filter uses a simple linear model. That's that AX plus BU you see. It's all straight lines. The extended Kalman filter, on the other hand, gets to use the real, curvy, nonlinear function, the F, to make its main prediction. That's way more accurate. But, and this is the compromise, to update the uncertainty, it still uses that straight line approximation. That's why we say it's not guaranteed to be optimal anymore. It's an amazing approximation, but it's still an approximation. In the real world, though, it works incredibly well.
So why does any of this matter? Why we just waded through all this stuff about bell curves and nonlinear systems? Well, because this idea, this predict and update logic, is one of the most important, most widely used concepts in all of modern technology. Seriously. I mean, this is not some obscure academic idea. This thing was literally developed to help navigate the Apollo missions to the moon. And today, it is the invisible engine running inside your phone's GPS. It's what allows self-driving cars, drones, and yeah, our AUV to work. It's used for everything from tracking targets to forecasting the weather and the economy. This is the fundamental tool that takes a messy, noisy, uncertain world and turns it into information you can actually trust and act on.
And it all comes back to that one, single, powerful idea from the very beginning. The hypothesis that you can actually represent uncertainty in a robot's position with a Gaussian with a bell curve. The idea that uncertainty isn't just some random noise you have to ignore. No, it's something you can actually describe, model, and work with mathematically. That is a total game changer.
And that really leaves us with one final big question. This beautiful little cycle of predict and update, of guessing and then correcting with new evidence, it's allowed us to navigate to the moon, explore the bottom of the ocean, and drive through our own cities. So the question is, what's the next big problem we can solve with this kind of thinking? What happens when we apply this same smart approach of guessing and correcting to things that are even more complex, even more uncertain, like the climate or the economy, or maybe even how ideas themselves spread through society?